Welcome to This Explainer. Okay, so today we're diving into one of the most fascinating and honestly most persistent mysteries in all of quantum mechanics. Now, if you've studied quantum theory, you already know it's famous for its weirdness, right? The spooky action at a distance, the incredibly precise mathematical predictions, but buried deep within those predictions is this very specific, reoccurring magic number. It's a number that standard quantum mechanics computes flawlessly, but it rarely actually explains. And that number is 2 times the square root of 2. So in today's explainer, we're going to be exploring a brilliant new framework that finally strips away all the abstract algebra to show us exactly where this number actually comes from. We're going to find its origin not in a bunch of complex formulas, but in pure, elegant geometry.
So here's our roadmap for today. We'll start with the historical origins, move into visualizing 3 geometric axioms, tackle the geometric derivation to crack that 2 root 2, and finally, make the leap from algebra to geometry.
All right, part 1, historical origins of the CHSH inequality.
Let's quickly track how a single philosophical question evolved into a hard, measurable number. It really kicks off back in 1935 when Albert Einstein, Podolsky, and Rosen proposed the famous EPR paradox. They were basically arguing that quantum mechanics just couldn't be the whole story. It felt incomplete to them. Fast forward to 1964, and John Bell brilliantly transforms this philosophical debate into testable math with Bell's inequalities. He showed that if the universe operates on local hidden variables, which is what Einstein was hoping for, there are strict statistical limits to how correlated particles can actually be. Then, in 1969, Clauser, Horn, Shimony, and Holt formulated the CHSH inequality. This was huge because it made Bell's theorem way more practical for actual lab experiments. And finally, in 1980, Boris Tsirelson proved the absolute maximum limit that quantum mechanics allows for the CHSH correlation.
Which brings us to the ultimate detective question of this explainer. You see, Tsirelson proved that the quantum maximum for the CHSH inequality is exactly 2 root 2. And sure, standard quantum mechanics using Hilbert-based axioms can easily compute this value. It spits out 2 root 2 perfectly. But it never explains why. Like, why this specific number and not some other value? For decades, it's basically just felt like a mathematical accident.
Moving on to part 2. Visualizing the 3 geometric axioms.
Okay, so we've got to start with our foundational geometric object here, the Bloch sphere. Geometrically speaking, the pure state space of an isolated single qubit can be mapped perfectly to the surface of a sphere. But here is the absolutely crucial detail. We are going to normalize this sphere so it has a radius of 1 and perfectly uniform Gaussian curvature, which we'll label as k equals 1. Now, why do we do that? Because this curvature is naturally supported by the foundational math of spin, specifically the SU2 Casimir operator. So it's not just some arbitrary choice. It is literally the natural intrinsic geometry of a single quantum bit. So we're building this whole framework on 3 really intuitive steps, or axioms. Step 1 sets up our arena, the geometry of the Bloch sphere, with that perfect curvature of 1. Step 2 handles our composite systems, basically saying the correlation between 2 entangled qubits is completely determined by the geometry of those single qubits interacting. And step 3, this one is just beautiful in its simplicity. It says a quantum measurement isn't some abstract, weird statistical collapse. It is simply a geometric projection. I really want you to visualize a measurement as just a vector casting a shadow onto the measurement direction. That's it. And this brilliantly illustrates how those axioms combine. When you take 2 maximally entangled qubits, what we'd call a singlet state, and you measure them along directions A and B, the correlation function simplifies beautifully. The correlation E of A and B ends up being exactly equal to the negative dot product of those 2 measurement vectors. No mysterious algebraic rules required here, just the geometry of angles and vectors in a perfectly curved space. All right, on to part 3, geometric derivation, cracking 2 root 2. Take a look at the CHSS operator here, denoted by capital S. At first glance, it looks like a ton of algebra, right? But look a little closer. Because we just established that correlation is literally just the negative dot product of vectors, this whole equation is really just asking a geometric question. We've got 4 measurement vectors on our unit sphere, A prime, B, and B prime. And the goal? We just need to figure out how to arrange these 4 vectors on the surface of the sphere to maximize the total value of this equation. In other words, it's asking, how do we arrange 4 sticks on a sphere so that the combined length of their shadows is as long as geometrically possible? Well, by applying the rules of spherical geometry, we can see exactly how to solve this puzzle. To max this out, the setup has to be incredibly symmetric.
First off, all four vectors must lie completely flat on a single two-dimensional plane cutting through the sphere, meaning they have to be coplanar. Second, they need to be spaced out at very specific, rigid intervals. 3 of the angles between these vectors have to be exactly pi/4, so 45 degrees, and the one remaining spanning angle has to be 3 pi/4, or 135 degrees. That is the absolute optimal way to arrange these vectors.
And boom, here is the wild part. When you take that mathematically perfect, highly symmetric coplanar configuration of vectors and you calculate their combined projections, you get exactly 2 times the square root of 2. It just naturally pops right out. It is the absolute maximum correlation amplitude you can physically achieve by arranging 4 vectors on a unit sphere. So you see, it's not a random mathematical accident at all. It is an unavoidable hard limit of the geometry itself.
Now, just to quickly tie up a historical loose end here. In experimental physics, you'll often hear people talk about the Clauser-Horn, or CH inequality violation. This is intimately tied to the CSH inequality we've been talking about. By simply shifting our new geometric CSH maximum of 2 root 2 through a standard conversion formula, we get the CH inequality violation. Mathematically, that shakes out to exactly the square root of 2 minus 1, all divided by 2, which gives us our famous experimental value of approximately 0.2071. It all connects back perfectly to that exact same geometric projection. Finally, part 4, the leap from algebra to geometry. I think this comparison really highlights the whole paradigm shift here. Under the old standard algebra framework, computing 2 root 2 honestly felt a bit like math magic. It just appeared as this accidental numerical product of the abstract rules governing Hilbert space. But when we look at it under this new framework of geometric reality, that number is derived as a strict necessity. It is the intrinsic projection of a sphere's curvature, specifically a curvature where k equals 1. It completely demystifies the bound.
And the implications of this? Absolutely massive. By bridging abstract quantum correlations with pure geometric information dynamics, it really highlights how fundamental that curvature of 1 is to virtual space. Plus, this framework opens up doors to interpreting even more complex quantum mysteries, like the I3322 inequality, which actually involves 3 measurement settings instead of just 2. It also paves the way for studying partially entangled states to see if we can spot observable deviations from standard models. Honestly, this framework is just beginning to show us its power.
I want to wrap up with this powerful conclusion directly from the source material. It reads, the Tsirelson bound 2 root 2 is not an accidental product of Hilbert space algebra, but a geometric projection of the qubit Bloch sphere under the optimal measurement configuration. This fundamentally changes how we view quantum non-locality. It forces us to ask a really deep question. If quantum entanglement and the strict limits of correlation can be completely explained by the simple, spherical geometry of vectors and shadows, what does that mean for the true underlying shape of our reality? Thanks so much for joining me on this explainer, and remember, keep questioning the geometry of the universe.